In this lesson, we will take a look at the frequency analysis and the buckling analysis. What we're going to do is just consider a very simple part and understand how to set up the problem for the frequency and the buckling analysis. We are also going to do the theoretical verification from the the equation based on the Euler's column formula for the buckling analysis, and also the equation for the fixed free condition to calculate the fundamental natural frequency for a simple cantilever beam. Okay, so about the natural frequencies, the frequencies at which the resonant response occurs under the right excitation conditions are basically the natural frequencies, and the knowledge of these critical dynamic frequencies is very important in the design and evaluation of the system that is subjected to the dynamic loadings. And also the static loads can also produce the instabilities for a particular combination of the geometry and the loading that has been applied on it. The buckling of a long slender bar in the axial compression is a very common example that is found in practical applications. So we're going to take a look at the example of a fixed free column and verify the answers with the Euler's column formula. Okay, so let's go ahead straight away and first do some theoretical calculations for the frequency analysis, and then we will take a look at how to set this problem up in the in the SOLIDWORKS. So as you can see, this fixed free column, it's fixed on one end and free on the other end. The length is 25 inches long, and the cross section is rectangular, ½ inch by 1 inch. And depending on what the orientation of the beam is, it's going to have multiple modes of natural frequencies in either XY plane or XZ plane. And you will have the different amplitudes of vibrations. Alright, so the simple equation for calculating the first mode of the natural frequencies for this case, you can calculate that by using the equation F1. The first natural frequency of vibrations is equal to 1.875 square divided by 2 pi times square root of E, which is the Young's modulus of elasticity. I is the area moment of inertia, G the gravity, then W, which is the mass per unit length, times L to the power 4. This equation, we can use it, and the answer you will get in the hertz. So if we consider the material for this particular problem, let's say we take the alloy steel as the material to find out the natural frequencies for. From the SOLIDWORKS materials database, we can see that the Young's modulus of elasticity is 30.45 10 to the 6 psi, so into 10 to the 6 psi. The length is given as 25 inches. The area moment of inertia, so I equals to bh cube over 12, and depending on what the values for b and h you take, depending on that, the natural frequencies will be different. So in this case, if we orient this column in so that I can be calculated as 1, let's say I the b equal to 1 and h equal to 0.5 cube over 12, so that's the I, and the value of G equals to 386 inch per second square. All right, and then finally W is basically mass per unit length, E, I, G, and L. So W. So the mass per unit length, W, is equal to M over L. And the easier way to find out this M over L value is if you just consider the density of this material. Let's say density equal to mass over volume, and volume we can express that as mass over the length times the area of cross section. So from that we can derive this M over L, and so this M over L equals to A times rho. So rho is the density, and so this is equal to the area of cross section is 0.5 times 1, so that's 0.5 times 1 multiplied by the density, and for the alloy steel the density is equal to 0.278, okay, in the appropriate units. And so once we get this value of the W, which is mass per unit length, as 0.5 times 2.278, substitute here, substitute all other values. In this case we will figure out the fundamental natural frequency is coming out to be 26.56 Hertz. Okay, and if we try to calculate the natural frequency in the other plane, meaning which instead of I equal to 1 times 0.5 cube over 12, if we change the orientation of this beam by 90 degrees, so we get 0.5 times 1 cube over 12. And if we plug in this value in this equation, we will get the natural frequency as 53.12 Hertz. Okay, so these are the theoretical calculations that we have that can be calculated, and we're going to verify this by doing this in the SOLIDWORKS. We need to see if we get the fundamental frequency value that is equal to 26.56 Hertz. So let's open the SOLIDWORKS and let's start a new part. It's going to be a simple geometry. Let's first make sure the units we are using are in the inches. I'm going to go to the front plane and create a rectangle, something like this. Let's use the dimension of the length as 25 inches, and this is equal to 1 inch, and we're going to extrude this by ½ inch. Okay, so once we have the geometry ready, then we can take it to the simulation study, and in this case instead of using the static, we have another simulation option that says frequency. So we're going to click on the frequency and then click OK. We're going to assign the alloy steel material. Then we're going to use the fixed geometry on one end, so that becomes the fixed free condition. And there is no external load here. This is the natural frequency of vibrations. So I'm simply going to just use mesh and run to get the different mode shapes. So by default it has given 5 modes, something that you can set it up by right clicking on the part or right clicking on the frequency file and go to properties, and here you can set how many frequencies that you are looking for from the analysis. So the mode shape 1, you can see it's 26.61, which is what we were able to verify that theoretically as well. And if you simply go on to the next shape, that is 53.13, again that is something that we had verified that as 53.13 here, and so that way we can verify these numbers very quickly using the theoretical calculations. So it's a simple problem to set it up. Sometimes the results are heavily influenced by what kind of mesh that we used for these type of studies. You can see the mode shape values here. Again, you can animate as well. For, let's say, for the first shape, you can animate it, and you can see that it is the XZ plane vibration that it is going through. The next one, if we see that this should be along the XY plane, so we can verify that as well. So that is in the XY plane. All right, so this is out of plane, or the as we switch that by 90 degrees, the moment of inertia calculations, then we can see that for that particular frequency the vibration will take place in the XY plane. Okay, so you can also find out or list the values of all the amplitude, or you can even define another mode or amplitude plot there. You can say list resonant frequencies, and so that's how you can get all the values of the frequencies for different modes of vibrations. All right, so that's the the fundamental frequency of vibrations that we can calculate for this simple model. And so with this, now let's take a look at the buckling analysis by using the Euler's column formula. We will be using the same geometry as we used for the calculation of fundamental frequencies for this column, which is fixed at one end and the other end is free. Now in the buckling analysis, what happens is that we want to see what is the critical buckling load that will cause this column to buckle when the load is applied in the axial direction in the compressive manner. Okay, so the way to do this buckling load estimate, we can take a look at the Euler's column formula. So let me first show that a column formula. So in the Google, again, if you want to type in the Euler's column formula and then visit the engineering toolbox link. So that's basically what the problem that we are looking at. So a column is fixed on one end, and from the other end the force is applied in the axial direction in the compressive manner, and the critical buckling load, or when the column will fail because of the buckling, when the critical load is reached, and this is the critical load that we want to find out by using this equation, n times pi square EI over L square, where F is the allowable load, or it's also called as the critical buckling load that will cause the this column to fail due to buckling. N is the factor accounting for the end conditions. So depending on how the end conditions of these columns are, you have to use the values of n. For example, if it is fixed on both ends, then n should be taken as 1, and something like that. So we're going to be modeling this last condition, end condition here, where it's fixed on one end and the free on the other end. So that means we're going to use the value of n as equal to 0.25. E is the modulus of elasticity, L is the length of the column, and I is the moment of inertia. Okay, so we're going to find out first what is the critical buckling load for the dimensions of the problem that we have. And so we can write down this equation as the critical buckling load F equal to n pi square E times I, divided by L square. Okay, so if we plug in these values here, n equal to 0.25 times pi square times 30.45 E6 or times 10 to the 6. We're using the same material, alloy steel, as we used in the previous case, multiplied by I, which is BH cube over 12. So 1 times 0.5 cube divided by 12 divided by L square. So L is 25, so 25 square is 625. And when you compute this, this number comes out to be 1252.53 pounds force. Okay, that's the critical buckling load, and the beam is going to or this column is going to fail due to buckling when this critical load is reached. And as we will see it in the simulation, as how the column will vibrate in the XZ plane. Similar to the previous one, if we change the orientation of the beam to find out the different mode of buckling, then this force, when we change the I equal to 0.5 times 1 cube over 12 in this equation here, and recalculate this critical buckling load, we end up getting the value of 5010.12 pounds force. Alright, so we're going to observe these two values for the critical buckling load, and then we'll come back here to understand what is the buckling factor of safety, and also how we can really figure out how to calculate this critical buckling load. Alright, so let's go back to SOLIDWORKS one more time. And for the same part, I'm going to start a new simulation study, and this time I will choose the buckling as my analysis, which should be listed under the advanced simulation topic. So let's select this buckling, click OK. I'm going to assign the alloy steel material, and then I will fix the part on the one end and keep the other end free to simulate the fixed free condition for the buckling estimation. Now we want to find out how much is the buckling load required so that this column is going to buckle and vibrate in that particular plane, but we don't know yet as how much is the critical buckling load. And in order to run this simulation, we still need to assign some value of the force here to run this simulation. So what's typically done is that we assign a something called as a seed force, which is typically equal to 1 unit in the compressive direction. If you're using the SI units, use 1 Newton, but if you're using the English units, then use the 1 pound force. Okay, so that's just a seed force to give us the idea about the load factor, which you will see it in a minute once we run this simulation. So if you click on the check mark and run this simulation, okay, you would notice that it gives you the mode shape and the load factor, which is equal to 1254.4. That is the load factor, and what that means is that to find out the critical buckling load, you multiply this load factor times the amount of force that we have applied. So from our theoretical calculations, we had looked at 1252.5, and from the simulation we get 1254.4. So the results match fairly well. If I animate this again, you can see that it's the buckling is it has taken place for the 1250. If there was a load of 1254.4, the beam would buckle and vibrate in the XZ plane like this, right? So that's the load factor of 1254.4, which we had estimated it using the theoretical calculations based on the Euler's column formula. Okay, so now this load factor is what the SolidWorks simulation reports. So in calculations, if we want to find out what is the critical buckling load that will cause the buckling on the component, is equal to this is in SolidWorks, as we can use this equation. So in SolidWorks, from the SolidWorks result, the critical buckling load is equal to the load factor multiplied by the amount of force that we have used. Okay, so that is the idea behind using the force F equal to 1 pound or 1 unit load. So that way, whatever is the load factor that we get from the SolidWorks is basically equal to the critical buckling load. All right, so we got we used F equal to 1 pound, and the load factor we got from the SolidWorks results was 1254. So 1254 times 1 equal to 1254, and so that way basically whatever is the load factor, that is the critical buckling load. Okay, so if we use let's say instead of F equal to 1 pound, let's say if we use F equal to let's say 2 pounds, okay, then the load factor that you will observe will be divided by 2. So in order to keep this critical buckling load as 1254.4 something, yeah, so 1254.4, the SolidWorks will calculate the load factor as 1254.4 divided by 2, which is 627.2. all right, so depending on whatever is the amount of force that you used, the load factor would be adjusted accordingly, and so that when you multiply the load factor times the amount of force you apply, that will give you the critical buckling load. Okay, so let's verify this real quick, that what if instead of 1 pound force, if we use 2 pound force, then does really the load factor is equal to 627.2. So what I'm going to do is I'm going to just quickly change this to edit definition. Instead of 1 pound force, I'm just going to use 2 pound force, and then rerun this analysis. And so you will see here the load factor is now 627.2, which we had estimated that it will give us the load factor of 627.2. So the idea here is that whatever the amount of force we use here times the load factor is equal to the critical buckling load. All right, so by default it has given us only the first mode of vibrations based on that the mode 1, but we can always add the further amplitudes by right clicking on the buckling properties. So instead of 1, if I just make it 2, click OK, run this study. So it's calculated that, but it's not really showing it here, although you can click on these arrows to show the next mode, but I can always define the amplitude plot and change this to 2, right, and then click OK. And so that way the second mode will be in the XY plane. Let me just change this back to 1 so that we can do a quick verification of this for the second mode of vibrations or in the XY plane. I'm going to rerun this study. And the second mode is coming out to be 5009.6 load factor, but the force was used as 1, so this must be the critical buckling load in the XY plane. I can quickly do the animation, so verifying that this is in the XY plane. Okay, and then 5009.6, which we had calculated earlier as 5010.1. so again, basically that's what the matching of the results with the theoretical calculations, as we can see there. All right, so that's the buckling study. That as simple as that, we can do it using the SolidWorks simulation. And one last thing before we close this topic is that the buckling factor of safety, I'm going to call that as BFS, as the buckling factor of safety. And you might have guessed it by now, as it's very simple to calculate the buckling factor of safety, which is equal to the critical buckling load divided by the actual amount of load that we apply. All right, so in a way that this buckling factor of safety is nothing but the load factor. Okay, it's just a different name that you can use it here. Okay, so it's the same equation, critical buckling load equals to load factor times the amount of force applied, right? So it's the same thing as that. So buckling, the critical buckling load equal to the buckling factor of safety times the load. So which means that the buckling factor of safety, or we can also call that as a load factor, equals to the critical buckling load divided by the actual load applied. All right, so if the critical buckling load was say 1254.4 and we apply the load of 1254.4, which means that the column is about to buckle, and so the factor of safety is equal to 1. So as soon as the load applied exceeds the critical buckling load, it means that there are, in all likelihood scenarios, that the column is going to buckle, because the factor of safety will go down below the 1. All right, so that is it for the frequency and the buckling analysis, and I'll see you in the next video.